Hello and welcome to another math video. Today we are talking about vectors and higher dimensions, which is a topic in linear algebra. So we can use a symbol, which is like a capital R, but with two vertical lines through it, to represent the set of all real numbers. And now what are some examples of real numbers? Well, we have numbers like 0, positive, negative 1. We can also have 10 over 3, which is 3.3 repeating, or numbers like pi. And then maybe it's easier to answer the complement of my question. What are some examples of non-real numbers? Well, those would be our imaginary numbers like I, which is the square root of -1, and complex numbers, so any sort of operation involving I, like pi plus 2i, for example. And then we also have R2, which is the same symbol, but with a 2 in the superscript, which is the set of all vectors with two real number components. And an R2 space you're familiar with is the XY plane. And then we can also have R3, which is the set of all vectors with three real number components. And maybe you're familiar with the XYZ space, where maybe you have some arbitrary point P with the components XYZ, and it has a corresponding standard position vector with the components XYZ. And maybe you're starting to see a sort of pattern where we have R, or you could say R1, and then R2, and then R3. What's next? R4, and then after that, maybe we have R5. Well, we actually have an infinite number of dimensions, and we can go all the way to Rn, which would be the set of all vectors with n real number components. And I can't really draw that one out for you or reference a space like I could with the XY plane or the XYZ space, but you can describe a vector, and we can say vector v, some vector v, and we can describe that vector that lies in the Rn plane, or the Rn space, by describing all of that vector's components from v1, v2, all the way down to vn. And though I can't draw the Rn dimensions, the fundamental vector operations, which we talked about in the last video, vector addition and scalar multiplication, are still going to work the same way algebraically. So if I wanted to add two vectors, we can say, we'll call the first one vector u, and we can list all of vector u's components, u1, u2, all the way to un, and we can perform vector addition with the v vector. So we're going to list all the v vector components, v1, v2, all the way to vn. And we still do that by just individually adding each of the components. So u1 plus v1, and then u2 plus v2, all the way to un plus vn. And then in terms of scalar multiplication, we still have the same thing. If we want to scale some vector v by some scalar c, we still do it the same way, where we're going to pull in this scalar to each of our components. So we have c times v1, c times v2, all the way to c times vn. So now why is this useful? Why do we care that we can have n dimensions or an Rn space? My question for you is, can you think of any concrete real-world examples where this is useful? We know R3 is useful. We know that 3D is the reason our universe exists the way it does, but let's not even go as far as Rn. What about R4 or R5? We can't draw those spaces, but why do we care that they exist? So here's one example that I could think of. Maybe we have this couple, Alex and Bob, and they each own shares of stock in Meta, Apple, Amazon, Netflix, and Alphabet. And let's say Alex has 100 shares in Meta. We'll say 50 shares in Apple, 20 shares in Amazon, 125 shares in Netflix, and 30 shares in Alphabet. And Bob has 25 shares in Meta, 120 shares in Apple, 100 shares in Amazon, and 80 shares in Netflix, and then 50 shares in Alphabet. And let's say Alex and Bob want to pool their holdings and see how much they have together. Well, how can we do that? Well, we can add the vector that represents all of Alex's shares, and we can call that vector A, with the vector that represents all of Bob's shares, and we can call that vector B. And now we're simply just doing vector addition, which we covered in the last video. And now would be a great time to pause and try it yourself. So let's start by writing down all the components for Alex, or the vector A. So we have 100, then 50, then 20, then 125, and then 30. And then for vector B, we have 25, 120, 100, 80, and 50. And now that we have the components for both of our vectors, we can do vector addition. And now we know we can just pull these components in to one vector and do the addition inside. So we'd have 100 plus 25, 50 plus 120, 20 plus 100, 125 plus 80, and then 30 plus 50. And hopefully you get 125, 170, 120, 205, and 80. And now this vector represents the total shares of each company Alex and Bob would have if they pooled their holdings. So together they would have 125 shares in Meta, 170 shares in Apple, 120 shares in Amazon, 205 shares in Netflix, and 80 shares in Alphabet. Now that's the example I came up with, but feel free to leave a comment down below with any examples you came up with, and maybe I'll use it in a future video. That's all for this video on vectors and higher dimensions. Thank you so much for watching, and remember to keep on trucking.